Okay, Assalamualaikum warahmatullahi wabarakatuh. Our group will present about Project High-Rise Buildings, Beijing Bird Nest Stadium. And this is our group members, Iza Atira binti Kuzaini, Nur Nazira binti Mas'ud, Wan Fatin Nasiha binti Syahidan, Nur Syamimi binti Muhammad Syariman, Muhammad Afiq Luqman bin Musa, and myself Arif Amirul bin Ibrahim. And our lecturer's name Dr. Muhammad Fikri bin Hasmori. So I will continue my next slide about introduction for Bird Nest Stadium, Beijing. Okay, Beijing National Stadium is situated at Beijing City's North Fort Ring on the southern part of the Beijing Olympic Green. It was designed by Swiss architect Jacques Herzog and Pierre de Meuron, winning the Pulitzer Prize, and by artist consultant Ai Weiwei. It is commonly called the bird nest.
Foundation system. The structure was consuming thousands of tons of concrete and steel. The weight of the stadium was 110,000 tons of steel that considered for a dead load. This building is synchronized on 38 meters of piling capable of supporting the horizontal force of the structure below the ground. The structure must be capable to resist a vertical load in a total of 56,625 tons. Selected the essential type of foundation, a light plate, to carry the overall load which distribute. The figures show the structural design of the foundation and the plate foundation. This Bratton Stadium was using cast-in-situ concrete profile, the most economical foundation that capable to transfer high load through the soil to the deeper, more competent soil or rock stratum is bore pile. To suit the nature of the soil, the competent drilling tool is selected to excavate the soil on site where ground conditions are unfavorable. For the construction of bore cast-in-situ pile, first set up or locate pile point on the ground. Second, boring process. Third is reinforcement placement. Fourth is bore cast-in-situ pile concreting.
Deep excavation. First is the diaphragm wall. The geometry of the primary elements forms a relation between the supporting elements, points at the ground level, and opening roof position, size, and shape. The moving roof was finally eliminated from the design, and the opening size should become bigger and more closely correspond to the seating bowl. The primary geometry was then developed into 3D portalized space truss, enabling the roof to follow closely to architectural form of the ball and concourse structure with rising to 60 meter and spanning the required 330 meter times 266 meter. The second is the machinery. So they use a bogie design. The bogies also either provide stability to extreme seismic event, and additional restraint was provided by sliding restraints transferring loads into the fixed roof structure. These tie-downs also transferred any uplift load induced by wind. Each bogie, typically weighing about 3 tons, would support the corners of the triangular roof panels. Drive system. The gradient of the curved track on a fixed roof is 10 degree at its steepest, mean that without a rack and pinion drive or winch driven system. A power railway type bogie system could not be operated reliably. Space inside the bogie to pack the former and the design advanced using a wire rope cable, which system is as this was the most cost effective option.
Structural frame system. It is constructed with two independent structures. The first one, red concrete seating bowl, and the second, outer steel frame. For the outer steel frame, it is constructed with steel lattice structure. The distance around between this structure is 50 feet. And the second, the stadium located at the most seismic zone, so that the focus for the design is to prevent the damage because of earthquake. And here you can see the figure show the 3D models of the steel structure that built by the architect. The concrete bowl. It is stands that holds spectators located between the balls. It is constructed as 8 different zones that have their own stability system. And third, it is precast concrete, so we can minimize the use of homework. The figure shows the view of the stadium. For the roof, upper part, it is used double-layer membrane structure which is transparent ETFE. For the lower part, translucent PTFE membrane fits on it, and it is also attached to the side of the inner ring. Homework system for installation of steel structure. The curved steel frame were constructed before, and then it is assembled on site, and the whole steel structure of interconnected sections was welded together. Steel structure support by 170 seat hydraulic jack during its construction. Removal of steel columns. It is standing on 78 supporting steel columns, and to get rid of the columns, hydraulic jacks were used. First one, this jack would first support the roof, and then the columns would be removed, and therefore the load would transfer to the jacks. Last one, it is allowing the structure to support its own weight.
Concreting method. So the curved steel frame surrounding the stadium, which is largely self-supporting, was phased in. This phase installation involved the interconnection of the section of the curved steel frame that were constructed in Shanghai and transported to Beijing for assembly and welding. The entire structure of interconnected section was welded together as the primary means of the interconnection used to assemble the entire surrounding structure. Upon removal of the supporting columns, used to facilitate the assembly of the interconnecting parts. So the challenge and the problem, the unusual structural form, the technical limitations and the ability of the company, the very long span of 313 meters that have caused the seismic design to differ significantly from that typical tall buildings in several ways. The Birdnest Road structure seismic design measures that normally meet the collapse prevention of the goal for tall buildings under the level 3 earthquake, such as limiting inter-story drift and detailing for ductility, were inadequate.
Facade. So basically, this stadium has a gross volume of 3 million cubic meters and is considered to be the world's largest enclosed space, according to the Arab Journal. The architect has created an open facade surface to allow for natural ventilation and lighting, which is the most important aspect of the stadium's sustainable design. The facade external surface has an inclination of approximately 13 degrees to the vertical. The room was separated from the sitting bowl to help make the structure resistant, or to help the structure safe, because of we know China is highly vulnerable to the earthquake.
This is wind load engineering. Rules of the International Association of Athletics Federation (IAAF) competition stipulate that information about wind speed must be available for athletics records up to and including 200 meter long jump and triple jump. Unless the wind speed behind the run average more than 2 meter per second in the direction of running, the record will not be acknowledged. Measurements were therefore also made of wind speeds around the tracks, and the result presented in the term of percentage of the time that gust windmill must access around 2 meters per second on the track, notably of the sprint and horizontal jump area.
Seismic load engineering, an essential design of earthquake engineering that should be used to the building structure be surrounded by some of the deadliest fault lines in the seismic design. The design proved that it greatly reduced damage, prevent collapse, and also will support the structure frame if the worst case concrete failed to happen. Third, each part of the structure was being isolated so that it could move flexible and independently in the earthquake. The structure will easily absorb the energy by its free movement rather than being broken into pieces by the earth tremor. For the seismic load for Birdnest Stadium in Beijing, China, for your information, Birdnest Stadium was located in one of the world's most seismic zones and also provide advanced seismic analysis undertaken to test the structure in various earthquake loading conditions. is being supported on a single continuous 5-foundation system. The whole structure is divided into 6 independent structures by movement. Both structure was an independent building that located the 2 lift posts eccentrical toward the back of the structure from 2 shear wall core, resisting both gravity force and flow diaphragm deliver usually lateral force to the structure.
Method of construction. First, material. 176 water-driven jets boosted the steel structure during its development, while the structure was not equipped for self-containment. A precision of 1 mm, the crane was built for holding 300 tons. The water-driven jets were evacuated without a moment delay to check the solidness of the structure of the arena. Second, crane and position. Little arm force of welder raising steel bars by 8 cranes, more than 300 feet tall, lifted over the cranes, lifting metal pieces as overwhelming as 350 tons to shape a cross-section of joint steel. Loading condition analysis and consideration. The stadium includes mainly of the loads of stadium's maximum occupancy, 91,000 people for the superload. While dead loads considered during the load were burden of the roof structure is 42,000 metric tons. Therefore, the weight of the stadium is 1,600 metric tons. First, analysis. 12-meter deep trusses of the main roof complex interconnected, forming a 3-dimensional truss network structure system. 3D structural analysis model was built to carry out static and dynamic analysis of the roof structure. The complete primary and secondary steelwork structure modeled as a skeletal space frame in Arups GSA software. Figure 13 shows the main components of the original roof design. Second, construction stage analysis. Phase 1. Construct 24 columns, facade secondary structure, the ring trusses within the middle, and therefore the primary truss with temporary support. Phase 2. Remove the temporary support after assembly of the primary trusses in section completion of the most structure. Phase 3. Construct secondary structure on the higher surface and facade strains. Phase 4. Install the pipeline for cladding structure, catwalks, light fittings, and drain pipes. Finite element analysis. Ignore this.
Next is fire safety. As we know, the stadium is steel structure. However, the stability of the steel decreases dramatically when temperature rises to a certain degree. So, all the seats at the upper end of the stadium are made of incombustible material, so that when a fire starts, the surface temperature of the steel will not reach 200 centigrade degrees. This stadium also has nearly 120 safety exits to make sure that everyone can find the nearest exit as quickly as possible. Chinese also have developed a special fire suppression system called water cannon, which scan the entire arena for fire and automatically shoot water to the fire if it detects.
Service distribution. And first, rainwater cycling system. The National Stadium's modern water using framework will utilize underground pools that handle up to 100 tons of water per hour. 80 tons of which can be used for irrigating, firefighting, and cleaning a coordinate way to lower the stadium's water utilization. And GE innovation is chemical free and meets rigid natural guidelines for indoor. Discuss quality and commotion controls. For the next and second, development of a multi-type wireless sensor network for the large-scale structure of the National Stadium in China. Okay, a multi-sort remote sensor organized WSN for basic well-being observing is created for the National Stadium in China. For the most part, no birds' nests. The stadium could be super large-scale building with for the 2008 Beijing Olympics division and can host more than 19,000 tenants.